Hey there, chemists. We're going to look at titrations in this video, which are carefully controlled neutralization reactions. Actually, they're carefully controlled reactions of any type. They could be redox, but we're typically going to see them with acid-base reactions, so we'll look at those first. Let's start off with looking at what happens when you add a strong base to a mixture of a strong acid. And if we monitor it by pH, think about what happens. A strong acid would initially have a very low pH. We'd eventually get to a point by adding some amount of sodium hydroxide in this case to get to a neutral equivalence point, so a pH of 7. And then if we kept going, we'd somehow end up at a very, very high pH, let's say up here in the 13s or so. But it's not going to be a linear trend. You do not get a graph that looks like this. In case, for reasons that you'll see in a moment, we get a nonlinear curve with a significant point of inflection where it changes slope. So low pH at the beginning, low pH at start, and certainly high pH at the end, or I should really say past the end. And then here, this is key, this is called the equivalence point. Equivalence point. And it is neutral because we are making a salt between the strong acid and the strong base. And when you have exactly an amount of base to react with however much acid you have, you should hit a perfectly neutral equivalence point. This is different than what you would see with the titration of a weak acid and a strong base. Here we're still in acid, so we're still starting at a low pH, but it's probably not going to be as low as in the single digit, or in the zeros or ones. It might be in the 2s or 3s. You will still have a very high pH at the end, but your equivalence point will not be neutral. It will not be 7, because a weak acid plus a strong base will make a basic equivalence point. So we're going to have some equivalence point that's in the slightly basic range. Your curve will still not be linear. It will actually sharply increase just a bit before it plateaus. Then you get to your basic equivalence point, and then it flattens out. So we have a basic equivalence point. I'll highlight that. And buried within this titration curve is actually everything we've ever done in this unit. So I'm actually going to use this as an opportunity to recap all the things we've done and zoom in on each section and show how you can get pHs at all these different points. Starting at the beginning, at the very beginning, the pH is based on just the weak acid. We haven't actually added any hydroxide yet. So all we have is some amount of HA, whatever that weak acid is. And we know that we can set up an expression that's Ka is equal to x squared divided by HA, where x is your molarity of hydronium ion or hydrogen ion. So that's just how do you get the pH of a weak acid, which we've done many times, and that's true at the beginning of a titration. Right in the middle, at the equivalence point, this is where the pH is based on the salt. This is a salt. And the pH is based on, this time, the conjugate base, the A-, which will have some molarity at this point in the titration, and that means it has a Kb. And we can set Kb equal to x squared over A-, but now here, x is a hydroxide molarity. Molarity of hydroxide. So not exactly the same as the beginning because we're now in its conjugate, but this is exactly what we did when we looked at pHs of salts. It's just the counter ion of whatever you made. What about at the very end? Somewhere at the very end, or frankly anywhere along this highlight plateau, here the pH we'll see is based on excess hydroxide. which is how you get the pH of something that's strong. You just figure out what the molarity is, you take the negative logarithm of it, and you're there. Maybe you subtract it from 14. There's no K values needed for this because it's all strong stuff. There's one other point that's worth mentioning, and it's this section that's after you begin, but before you hit equivalence. Not up here, but just this plateau here. This is called the buffer region. It's anywhere after we've started and prior to equivalence. And here, the pH is based on the buffer equation. So, we could say that the pH is equal to the pKa plus, let's make some space, the log of the base, meaning the conjugate base, over the original acid. And that's true anytime we're in this region. So those 4 points of the titration curve we're going to see today, but hopefully you'll realize, oh, it's just a review of everything we've done before. Regular old weak acids, buffers, salts, and even strong acids and bases. There's one more thing worth annotating on these titration curves, and it's indicator molecules. It's hard to tell in the lab when you hit an equivalence point, so we use special molecules called indicators that change color based on their pH. You just use a small amount of it, but they're very sensitive to these changes in pH. For example, if I wanted something that changes color right at equivalence, I would probably use what's called bromthymol blue. Bromthymol blue is very yellow anywhere in the low pH range, anywhere, let's say, 6 and under, but it's quite blue anywhere in the high pH. So I can tell when it changes from one color to the next where my equivalence point is, because the equivalence point is hopefully right at that pH change. It's really over a range of pH, so I should go back and maybe make this sort of more multicolored. It's kind of greenish in the middle, actually, between 6 and 8. That's what you see with bromthymol blue. I'll just label that bromthymol blue. Most chemists should know that as a good indicator to use for acid-base titrations with a neutral equivalence point. What if I don't have a neutral equivalence point and have a basic equivalence point? Well, then we want an indicator that changes color in the basic range. And the most common one for that is called phenolphthalein. Phenolphthalein changes color from colorless to pink up in the basic range. It's actually not colored in a low pH, but once you hit a basic pH, phenolphthalein, spelled like phenol, and then PHTHALEIN, goes to a nice pink color once you hit a fairly basic pH. So we choose appropriate indicators based on what kind of titration we have. Okay, now let's do some quantitative studies with titrations, one strong and one weak, and we'll see how we can recap everything we've done in this unit, starting with a strong acid and adding a strong base. What's the pH after we add certain amounts of base? Well, let's think about the reaction that actually happens. We have a strong acid, H plus OH minus, and that just becomes water. First, let's do the stoichiometry. How much do we have of each thing? We have 50 mils of 0.2 molar H plus, so I have 50 mils of 0.2 molar H plus, and I have 10 mils so far of 0.1 molar hydroxide, so 10 of 0.1. So that means I have 10 millimoles of H plus and only 1 of the hydroxide. So we are at a limiting reactant problem, but it's a 1-to-1 ratio. You're going to lose all of the base, and you're going to lose a stoichiometric amount of the H plus. Yes, I'm going to gain some water, but it doesn't affect the molarity of H plus or OH minus ions appreciably, so I'm not going to factor in that 1 millimole of water, we could, but it's not really going to make a difference in the total volume. So all I care about is what's my concentration of H plus at this point. Well, it's this leftover 9 millimoles divided by a total volume of 50 milliliters. So 9 divided by 50 plus 10 is actually 60, and I get 0.15 molar. The pH is therefore just the negative log of 0.15, and we get 0.82. So I'd like you to hit pause and see if you can figure out what happens with the same amount of starting acid, but this time after 150 mils of 0.1 molar hydroxide. What would your pH be at that point? Okay, let's see how we did. It's the same reaction. It's still H plus OH minus makes water. We still have 50 times 0.2 molar H plus, but now I have 150 mils of the 0.1 molar hydroxide. I've still got 10 original millimoles of H plus, but now I have 15 millimoles of hydroxide. So this time I'm actually limiting H plus and excess hydroxide. So I'm going to lose all 10 of the H plus and lose 10 of the OH minus. So now my H plus concentration is appreciably 0, but my hydroxide concentration is what's left over. So my hydroxide concentration is the remaining 5 divided by the total volume of 50 plus 150. So my OH concentration is 5 divided by 200, which is equal to 0.025 molar. And my pH is going to be 14 minus the pOH, which is negative log of 0.025. I plug that in, I get 12.40. Makes sense. We are excess base. You should have plenty of hydroxide ions and a high pH. That's how you handle strong acid and strong base titrations, and those are frankly not that interesting. They don't involve equilibria, they're a little bit too easy to solve. So now let's get fancier, let's look at weak species. Let's do the same thing, but let's talk about weak acids and bases. So here we have a weak acid, it's got a Ka value, we're adding strong base, and we're going to get the pH at different time points at the very beginning, after some base has been added, after more, and even more. And you'll see that this recaps everything we've done with acid-base chemistry. So at the very beginning, we have no base yet. We're all acid, so all I need is the Ka value. Ka is x squared over the concentration of the acid. That's it. That's all we have to do. So I know the Ka, I know the molarity of the acid, so 1.8 times 10 to the minus 5 is equal to x squared over 0.10 molar. I simply solve for x. I get 0.0013 molar. This is a Ka, so that is my H plus. So my pH is just the negative log of x, which is 2.87. This isn't even a titration problem. It's just what's the pH at some solution of strong acid. Didn't even need the volume. But now let's talk about what happens after we add some base. After we add some base, some reaction occurs. So let's write an abbreviated version of that reaction. Ha plus hydroxide forms A minus and a water molecule. And now let's list the stoichiometry between each thing. We have 50 mils of 0.1 molar of the acid, and at this point we are 40 mils of 0.1 molar base. So that's 5 millimoles reacting with 4 millimoles. We are limiting in base. You'll lose all of it. You're going to lose a stoichiometric amount of the acid and have 1 millimole left over. So where are we? We have 1 millimole of HA. Well, wait a minute, we also made some amount of our conjugate base, didn't we? I gained 1 of the A minus. So we actually have some amount of HA and some amount of A minus, which means we are in a buffer. If you have an appreciable amount of each part of the conjugate pair, you get to go right to the buffer equation. So the buffer equation says the pH is the pKa, which is the negative log of 1.8, 10 negative 5, plus the log of the ratio of the conjugate pair in moles or molarity, plus the log of the, I'm going to use moles. How many moles of each thing do we have? We actually gained, oh, whoops, let me go back. We did not gain 1. We gained 4 millimoles of A minus, didn't we? Not 1, but 4. Because we reacted 4, we gained 4. So our ratio of our base to acid is 4 to 1. Useful to use moles. I could use molarity. It would just mean I divide both of those numbers by 90, and then I get the same thing. So when I plug this in, negative log of the Ka, I get 5.35. So there's how we get the pH at some point after we started. We are in the buffer range. We have yet to hit what's called equivalence. And speaking of, I'd like you to hit pause and see if you can figure out what to do with the next one. Now we're at 50 mils of base. Write out the reaction that happens, what's left over after the reaction happens, and see if you can use that to figure out what molarities of what ions are important and how to get the pH. Okay, let's write out the stoichiometry. Welcome back. It's the same reaction. HA plus OH minus makes A minus plus water. We still have 50 mils of 0.1 HA, but now we have 50 mils of 0.1 OH minus. I have 5 millimoles of each. So I lose 5 from each. I have nothing left over on the reactant side, but I gain 5 of the A minus. So that's my significant species. We are now in all A minus. This is now a base. This is like the pH of a salt, or really just the pH of a weak base. So I have some weak base, A minus, plus water, reversibly forming HA plus OH minus. If it's a basic species, it has a path to make hydroxide. That means it has a Kb value. So I need Kb. Kb is equal to x squared over the concentration of the A minus at this point. Kb is Kw divided by the given Ka. I'm just going to write it out. I'm not going to solve for it. I'll just write out what the numerical values end up being. And that's equal to x squared over the molarity of the base at this point. What's my molarity of A minus at this point? Well, we have 5 millimoles of it divided by 100 milliliters total. So in this denominator, I get to put 5 over 100. There's my equation to solve for x. You solve for x, I get 5.3, 10 to the negative 6 molar hydroxide. And when I solve for the pH, I'm just going to write it's 14 minus the pOH. So you take the negative logarithm of this number and then subtract from 14, you get 8.72. Makes sense. It's basic. We should indeed have a basic equivalence. Basic equivalence. Okay, one more. Now let's talk a little bit more base. Now we're past equivalence. What do we do? Let's start by writing the same reaction. HA plus OH minus makes A minus plus H2O. I consider all of it as if I'm starting from the beginning. Now we have 5 millimoles of HA, but here I have 6 millimoles of hydroxide. I'm going to lose all the HA. I'm going to lose that much of the hydroxide, and I'm going to gain that much of the A minus. So once again, we have some A minus, but we're also in a mixture of hydroxide. So I can write the same equilibrium A minus plus water, what's A minus doing? Well, it's reacting with water to make HA and hydroxide. But if I think about my rice table, or my abbreviated rice table, I don't just have an amount of A minus, I have an initial amount of hydroxide too. What's my initial amount of A minus? Well, it's 5 millimoles divided by 110 milliliters, subtracting some amount. And then my HA is going to be some amount of X. My hydroxide is not just X, it's X plus how much hydroxide I already have, which is 1 divided by the same total volume, 110. Now this is the same equilibrium as what we have in the previous part, so I get to use the same KB. So KB, which is KW divided by the Ka, is equal to HA times OH minus divided by A minus. So that's X times X plus 1 over 110 divided by 5 over 110 minus X. That's big. We could factor that out and solve for stuff, but let's get smart. This K value is going to be small, 10, negative 10, roughly. So I don't know how much I lose from this 5 over 110, but it's probably not much. Likewise, compared to the 1 over 110, I probably don't gain much. So as we've done with every single one of these problems, we can get rid of that minus X and we can get rid of that plus X. So this turns into just X. And then if you look at it, it's 1 over 110 divided by 5 over 110. This just becomes X over 5. This whole thing simplifies down to just X over 5. So I can solve that very quickly as a linear. X turns out to be 2.8 times 10 to the negative 9. Now what's X? Careful. X is HA. X is not the hydroxide concentration. The hydroxide concentration we defined as how much we already had from the excess plus whatever this new little bit is. And check it out, it's hardly anything. So the hydroxide concentration is going to be the X, 2.8 times 10 to the negative 9, plus what I had in the beginning, 1 over 110. Now 1 over 110 may not sound like a lot, but it's a lot bigger than this number. So this just equals 1 over 110. In fact, we already made that assumption back here, and it's a safe assumption. That X value is indeed negligible compared to 1 over 110. So we went through a lot of work for nothing. We don't even care about this little bit of A minus. The pH is only going to be based on that excess hydroxide. So if the hydroxide is 1 over 110, we can turn that into a POH, which we can turn into a pH, and I'm just going to write the final answer. I'll let you check on your calculator. You get 11.96. And if you look back up to our summary at the beginning, we said this already. At the very end, the pH is just based on hydroxide. Well, really, that's true anytime you're past equivalence, because it only takes a few more drops of that base before you spike in pH, and then you get to a very basic pH. Supposedly, if it was just a fraction of a milliliter past it, yeah, then the A minus would be significant, but most of the time that's not true. You're going to be asked to solve for it when it's excess hydroxide. Okay, that's what titration curves look like, and that's how you mathematically solve for the pHs at the beginning, before equivalence, at equivalence, and even way after equivalence if need be, and how it basically summarizes everything we've done in the acids and bases unit.